Hello, topic of this video is density functional theory, so called DFT. Have you ever heard DFT? DFT is computational quantum mechanical modeling method to investigate the electronic structure. In this video, we will talk about history and application of DFT. Let's start.
First of all, let me introduce about history of DFT. To understand the properties of materials theoretically, it is essential to solve quantum system of materials. Solving quantum system means solving many-body Schrödinger equation. First term means electron kinetic energy. Second term means atomic nucleus kinetic energy. Third term means interaction between atomic nuclei. Fourth term means interaction between atomic nucleus and electron. And the last term is interaction between electrons. However, solving many-body system takes a very long time and needs huge computer memories. So, actually, it is impossible to solve this problem. To solve these problems, many approximations and theories are needed. First, Born-Oppenheimer approximation is needed. Born-Oppenheimer approximation means that nucleus is fixed because the atomic nucleus is much heavier than the electron. It means that solving many-body Schrödinger equation can be reduced solving many electrons Schrödinger equation. Next, Weinberg-Kohn theory is base theory of DFT. According to Theorem 1, the external potential is a unique functional of the electron density. Second, the functional that delivers the ground state energy of the system gives the lowest energy if and only if the input density is the true ground state density. That is, we can use the electron density instead of solving the many-body wave function. The Kohn-Sham equation is an equation that solves a real DFT. If the density functions of the actual electrons and the imaginary free particles are the same, the total energy determined by the density function is equalized by the Weinberg-Kohn theory. Thus, he has changed the interacting particles into the problem of no interacting virtual particles that is easy to handle. Then, the many electron wave function is mapped to several wave functions of one electron, and the following Kohn-Sham equation is solved. The first term of potential is external potential, and the second term is electrostatic interaction between electrons. Third term is exchange correlation potential occurred by exchange each electrons. Here we have to approximate because the exchange correlation potential does not exactly what form it has. There are several ways to approximate the exchange correlation potential. First, the LDA assumes that the density is the same everywhere. Because of this, the LDA has a tendency to underestimate the exchange energy and overestimate the correlation energy. The errors due to the exchange and correlation parts tend to compensate each other to a certain degree. To correct for this tendency, it is common to expand in terms of the gradient of the density in order to account for the non-homogeneity of the true electron density. This allows for corrections based on the changes in density away from the coordinate. These expansions are referred to as generalized gradient approximations. There are many other ways, but the results different depending on how the exchange correlation energy is approximated.
By the solving quantum equation, we can obtain atomic structure, total energy, electron density, energy level, stiffness tensor, and wave function, and so on. Therefore, it can be applied to various materials research according to the properties to be explored: electronic structure, energetics, kinetics, dynamics, and so on. These applications can be broadly categorized into electronic structure and energetics and thermodynamics. The electrical and electronic properties of semiconductors and metals can be understood by representing the electronic structure of the material. In other words, the energy band structure and density of states. The energy band means that the energy level, which is the solution of the quantum equation, is drawn as a function of K point, which is the quantum number of the crystal. The density of states describes the number of states per an interval of energy at each energy level available to be occupied. For example, we can think of the case of KMO. The basic constituent unit of this material is an MO6 octahedron as shown in figure A. An isosurface of an electron density on the optimized structure is shown in figure B. Figure B shows that K atom, low electron affinity, loses electrons, and the electrons are mainly contained in the center of 4 octahedrons in the form of a cylinder. Figure C shows the energy band structure. The characteristic of the energy band structure is that 2 energy bands pass through the Fermi level, and these energy bands change mainly only in the direction of the MO chain. This means that electrical conduction occurs in this direction. In many cases, the important thing in studying material properties is finding an energetics or thermodynamically stable structure. In this case, it is important to compare the total energies of the various possible atomic structures rather than the detailed electronic structure or wave function characterization. For instance, we can think of the case of silicon. The left figure shows the relative stability of the pressure by comparing the total energy of the different structures of silicon with pressure. The diamond structure is more stable at atmospheric pressure, but the phase transition to the beta-tin structure occurs when the pressure is applied from the outside. It was a presentation on density functional theory so far. Thank you.